Welcome everyone to a new episode on the Shannon channel. I'm really happy to have one of the family today to give a talk. It's Roy Yates from Rutgers. And Roy is going to talk about the age of information, or as he usually calls it, age. So Roy is going to talk about age, and we're all going to listen. Thanks, Roy.
Thank you, Salim. So should I start my talk and my slides, or should we just sit here and chat for a little bit?
I think we should start your slides.
Okay. All right. So all right, I'll try to do share screen again. Share. And I follow Serge's instructions and go to full screen. Okay. All right, so I've gotten kind of comfortable with making presentations that are recorded without any audience. And what I find is your voice is different when you do that. And I'm not sure whether this will be like the kind of thing where you're not here, or the fact that I see your faces here makes it more like the thing where you are here. The other thing I guess I'll say is that I feel like this subject seems now wrong. Like somehow all of this quarantining and isolation is like the opposite of timeliness, right? We're like, all the stuff we have thought was really important for timeliness seems like the wrong thing. In fact, we should be, we're interacting with each other in kind of in real life in infinite time, right? Like it might be forever before I actually see all of you again in person. All right, so with those stupid thoughts, I'll start my real talk. So this talk is about age of information in networks, and it's actually a kind of a presentation of a paper that a new version appeared on Archive, and in fact the journal version will appear in IT transactions anytime now. It was uploaded and accepted and all that, and this is kind of the future where you do a video to advertise to let people in an hour find out what your paper's about. So, so in any case, low latency applications before quarantine seemed like they were becoming very important. You had vehicular safety message systems that cars would exchange messages, or mission critical IoT with machine-to-machine communication, virtual and augmented reality systems, and remote access, and other kinds of cloud-based systems. And these systems have kind of real-time delay requirements. Like, for instance, vehicular, typically you would like messages to be delivered with 1 millisecond delay. And these delay requirements are physical things. So for instance, in a vehicular system, a car moving 36 kilometers per hour, like in an urban environment, is moving 1 centimeter per millisecond. And if you know a car's position 1 millisecond ago, you would know its position within 1 centimeter. If you're building a virtual reality system, if somehow you move your head and it takes more than 10 milliseconds for the system to respond, it makes people seasick. So you have to have the system respond quickly in just a few milliseconds. And similar kinds of timing constraints exist for remote access and multiplayer cloud gaming. Okay, so I got started in this area maybe almost 10 years ago. Sanjit Kaul introduced me to these problems. He was Marco Grudiser's grad student at WinLab, and he was interested in hundreds of cars on the highway, and having those cars exchange vehicular status messages. And this work was kind of initially kind of tightly coupled to a vehicular communication standard called DSRC. But gradually over time, we found kind of that was less interesting than the more general problem. So in this application area, the messages would exchange, the cars would exchange updates, and you wanted those updates to be timely. So the thing we found, though, was that we were using a timeliness metric, and we didn't really understand how that metric works. So in a very simple setting, you think about two cars. The red car sends updates to the blue car. They have timestamps, and they pass through some kind of a network or a service system. And the blue car wants the newest state information. And the metric we were using was, what is the age of the most recent update received at the blue car? So conceptually, you can now think of the red car as a source, and he submits updates, these up triangles. And later, those updates are delivered to the blue car, who is a monitor. And we label them with down triangles to say they've been delivered. And you end up with this stochastic process that looks like this sawtooth. And I think, do I have a mouse that appears on your screen? I do. Okay.
Yeah, we can see it. Yes.
Okay, so I should have moved it off the side. Okay, so at some time 0, nothing has happened, and the age has some value of the most recent update, and the age grows. And then at some time here, an update is inserted into the system by the source, and the age continues to grow. And it grows because it hasn't been received yet. And then at a later time, this time here, the update is received, and now the age drops. And what the age drops to is exactly the age of this timestamp update. It was created at this time, and after time capital T, it was delivered at this time. And now the age of the system is exactly the age of that update. And then nothing happens, and the age grows, and another update is produced by the source. And then eventually it's received, and the age dropped, and this process simply repeats again and again. And so this is an example of where the updates are kind of few and far between, and the age grows a lot. It gets very large before the update is delivered, and the age drops again. So the update is actually going through the system fairly quickly, but between updates, the age gets large. So that says, oh, maybe you should increase the rate of updates. And so now you imagine a situation where you have 3 updates: the red, the yellow, and the blue update, one after another. And the red update goes into the system, and the age grows. And here the red update is received, and the age drops. And now the age grows. And now the yellow update, which went into service after the red update here, it's delivered now, but now the age doesn't drop very much. And it didn't drop very much because the yellow update got stale waiting behind the red update. So congestion in the system caused the red update to become stale. And similarly, this blue update also doesn't reduce the age much because it became old behind the red and the yellow, update. So we see here that high update rates cause queuing delays, which is bad. So this prompted us, this is now like 10 years ago, to look at this stochastic process of this age sawtooth, and to say, let's try to understand how we can have this process be small. Like, we really want the age to be low. We want the monitor to have recent and timely knowledge of the state of the source. And we know that high update rates are bad because they cause congestion, and low update rates are bad because you get infrequent updates and your knowledge, your timeliness is out of date. And so we formulate, how do we minimize this average age? So you can solve that problem by kind of decomposing this sawtooth into blocks that look like this gray polygon on the screen, and you know, you're accumulating the area under the curve and dividing by time, and a little bit of work and some sort of gentle assumptions on ergodicity allows you to arrive at an average.
You can solve that problem by.
So somehow I'm hearing a little echo, but I'll keep going. So you find this average age, which has to do with the arrival rate of updates, and it has to do with the second moment of the inter-arrival time. And then it also has to do with this this correlation between the inter-arrival time and the system time of an update. So this term, this correlation term, is the tricky one, because the inter-arrival time y between two updates and the system time t of that update tends to be negatively correlated. If you wait a long time before you put something else in the system, the system time of that update will be small, because you've allowed the system to become less congested. So you can analyze this formula for lots of sort of elementary service systems. So we started with things like MM and MD1 queues, and we see that it kind of confirmed our intuition. So looking at this blue curve for the MM1 queue, you see, oh, when the arrival rate is small, the age is bad, and it's bad because updates are injected infrequently. And over here at the far right side, you see the age is bad because of congestion, that the system is, updates are getting backlogged in the system. Same thing is true for MD1 and DM1 queues. If you look at MD1 queue, you see, oh, when the update rate is low, the age is also bad, simply because of updates being infrequent. But these systems do better at higher load, because there's kind of less randomness and less congestion from those system models. So the key thing to think about, though, is that in fact those notions of age as a delay metric are different than the traditional view. The traditional view is you have this notion of delay versus rate, and you think about the rate at which you can submit packets to a system, packets that are updates, and you increase that rate, and the delay will increase and eventually blow up as you approach some capacity. So sort of an old school notion of delay, or a notion of delay for these update systems, is that you want to submit as fast as you can, but delay gets worse as you do. And here we have something really different. We have a system, and because our goal is timeliness, we see something different. We have a system where low arrival rates are bad and high arrival rates are bad. And instead of this kind of everything gets worse with the increasing rate, we instead have systems where there's some optimal rate at which to submit updates. Okay, so I'll just make a few comments here that age is this kind of application layer end-to-end metric, and it's kind of a proxy for application-specific performance metrics. You maybe would like to know the exact position of the car, or have an estimation error on the position of the car, but here what we're doing is we're using the how out of date an update is as a kind of a proxy for say a precise position metric. So the other thing is that this is useful because networks are good at understanding timestamps. Networks are generally bad at embedding application-specific metrics, but packets have historically always had timestamps, and sort of exploiting that within the network is something that's quite feasible. The next point is that age is not completely new. There's been a literature of various places where if you search that these sawtooth processes have been seen going back to the 90s. But what's sort of the interest, I think, is just because low latency applications are now emerging that kind of bring back a focus. So finally, this notion of the age metric suggests redesigning the network in the following way. So for instance, here we have the same M something one systems, and we have the MM1 first come first served, and the MD1 first come first served systems, and these are the curves we had before. Now we have this green curve where we consider a last come first served system, and without preemption means without preemption in service, but with preemption and waiting. So the newest update goes to the head of the queue, and now what you see is that when you increase the arrival rate, things keep getting better. And what's happening here is that you're throwing away the outdated updates, and you're always serving when the server becomes idle, the newest, freshest update. And this idea of discarding the old and the outdated stuff is kind of key to reducing age in these systems. So the sort of the general conclusion here is that queuing is usually bad, and you shouldn't waste your effort on old updates if in fact your goal is to be timely. So the next point I want to make is that there's this number 2 down here, and all of these curves are above it, and this 2 is called the just-in-time lower bound, and it's a lower bound to the age that you get by getting rid of all queuing. Just as a server completes delivery of an update, you insert a fresh new age 0 update into the system. And if you do that and you have exponential service, your lower bound in age will be 2 with suitable normalizations. And in some sense, we felt for a long time that this just-in-time lower bound was optimum. And we felt that until we looked at an alternate system. So consider a sensor has a network interface, and then the sensor offers updates to this monitor, and there's some service time Y associated with delivering these updates, and now we consider the possibility of the sensor knowing this network state and deciding when to submit updates. So for instance, the sensor could do kind of updates at the maximum possible rate, which will be this just-in-time rate. Just as an update completes service, the sensor immediately gets a response that the update is delivered from the monitor. That's idealized, but useful as an assumption. And then it inserts another update into the system. And when I started to look at this system, I thought this was the optimal minimum age system, but it turns out that was wrong. In fact, the optimal updating policy for this sensor should be lazy. And it's lazy in the following sense, that when an update is delivered, the sensor learns this prior service time Y, And depending on the value of the prior service time, the sensor should wait before submitting another update. So in fact, the sensor should wait for some time beta minus y with a little plus, right? Which says that if y is small, then the sensor should wait for a time beta minus y before submitting another update. This beta acts as a minimum inter-update time, and the sensor should only follow the just-in-time policy to immediately submit if the prior service time is large. And at the time this was observed, it was quite surprising. I, in fact, thought it was a mistake, and spent several days trying to figure out where did my analysis go wrong, where did my MATLAB go wrong, before realizing that in fact there's something quite different here. And what's different is that is the intuition. Okay, so we have a slide here. They're not optimal. The intuition is in fact as y gets small, the prior service time. If the prior service time is very small, then the monitor has very timely information about the state of the sensor. And at that point, a new update doesn't decrease that timeliness very much. In fact, what you're doing is you're using the network resources if you immediately submit a new update to deliver a new observation that is almost the same timestamp as the previous one. So as the prior service time goes to 0, just-in-time updates lack novelty and become worthless. So what this lazy updating does is it avoids wasting service resources on worthless updates. So this idea was kind of fully developed in a paper by Yin Sun and Elif and myself and others that appeared a few years ago in the IT transactions. So since then,
I have a question. So this is very interesting, and I don't claim that I understood it completely, but is it true that you're making sure that there's no one waiting in the queue, right? That's what,
right.
And you thought, well, if no one is waiting on the queue, then this is the best thing. Like once.
Right, you should always keep the server busy. That if no one's waiting, the initial work was like, well, like you don't want to waste the server, but you also don't want to cause queuing delays at the server. So these just-in-time policies got rid of the queuing delay, and I thought, okay, that's as good as you can do. You don't waste the server being idle, but you also don't have any queuing. But it turns out that's actually wrong. Like in fact, if your previous update was delivered very quickly, right? If you immediately then inject a new update, its timestamp will be almost the same as the prior one. And when it's received, the age reduction is small, right? And it'll be too small to be worth the effort to use the network to transmit it.
But here,
network.
And the problem, there's no like networking cost, like there's no service time cost. So this is.
When you say no service time cost, I'm not sure what you mean exactly.
So when you say, for instance, the problem, as far as I understood, the problem, the way it's formulated, you don't care about how much. You just care about the time at the what you call the monitor, right? You don't care what happens in the network.
The age of the monitor.
Yeah.
Yeah, and so in this problem, you can submit as fast as the service facility allows. You can keep the service facility fully busy all the time, but that in fact is not optimal. You are better off waiting. If somehow your next update has almost the same timestamp as the thing that was just delivered, you should wait until you have an update whose novelty is measured by the age reduction it offers, has more value.
Okay.
Yeah, it was quite a surprise to me.
Yeah, it is very surprising. Yeah.
So in any case, this was
And do you
maybe
know
20.
beta? Is beta easy to compute?
Yeah, it's just like a Lagrange parameter. It's not so easy. In some settings, this is a diversion. When I got started in this work, I thought of the beta as like I used it to enforce a maximum rate constraint at the sensor. Like it reflected maybe an energy constraint of the sensor. And then I found out as you relax that constraint, right, you still didn't increase the rate. So in fact, it just is a free optimization parameter. So this idea is done quite carefully in this paper by Yin Sun. He's quite thorough. So since then, I've worked on a variety of problems to try to apply this idea of age in a couple other settings. So for instance, one of those settings is replicated storage, where you have a source and it updates a distributed database, and you have clients that read from multiple servers in this distributed database. And what you would like the clients, when they have a read, to have the most recent update from the source. So one approach to this is to guarantee consistency using a quorum mechanism. So in a quorum mechanism, the source makes sure that the latest information is written to some subset of W nodes, the right quorum, and the client reads from R nodes. And if you make sure that W plus R is bigger than the number of mirror servers, then in fact you're always guaranteed to get the latest read. On the other hand, if you look at Google and Amazon, they forfeit strict consistency to have systems run faster. People have business-oriented publications will report things like Google saying an extra half a second search delay cuts traffic by 20%, and Amazon will talk about extra latency costing them sales. And so it got us interested in this question of like, how does data consistency influence the freshness of the reads? So to look at this problem, we think about a system where content is written to all the nodes, but the write then is committed as soon as the source gets a response from W nodes, and then the read goes to all of the nodes from the client, but the client only waits for the responses from R nodes. And if W plus R is greater than the number of nodes, then you have a strict consistency. But in fact, with respect to age, it's not clear that strict consistency is good. So in fact, what we observe in all of these figures, where you condition on the number of read nodes R for a system with 100 nodes, is that strict consistency costs you in terms of age. So you can calculate the average age of a read at the client, and you get a curve that kind of looks like an age curve, and this is it's as a function of the number of write nodes that you wait for the source to write, and invariably you operate with less than strict consistency, and the reason is simply because when the source decides it's going to wait for W nodes to confirm the write, right, a larger number, it can't produce another update until then, right? It creates delay, and in fact, you'd be better off having the source abandon a write and only have some of the nodes updated, and then move on to the next node, to the next update. Another problem we've worked on is timely compression problems. This is also with my student Jing Zhang. And in this system, you think about a source symbol generator. It generates symbols x1, x2, and you pass these symbols to a lossless encoder that generates a binary stream. And that goes into a FIFO buffer. And there's a bit pipe over 8R, and then a decoder. And then at the output of the decoder, you end up recreating these source symbols. And the idea here, so first I'll say this system model was developed by Cheng and Sahai some time ago, 07. And from an age perspective, the way we think about this is that each symbol is an update. And we're interested in how does this lossless encoder work in order so that the age at the receiver is as small as possible. So, and essentially age becomes a decoding lag. So in fact, we've have a solution to this problem for encoder decoder design for a minimum age. We developed age optimal block codes for this lossless system. Another application we've
So,
looked
Roy,
at.
a quick question: when you say age
Yeah.
optimal block code, does that mean the code design is optimized, or the rate is, or the block size is optimized?
Oh, so you have to fix the block size for the source, and then, for instance, like the thing you might ask is, well, how does a Huffman code work? Is a Huffman code optimal for some block size? And the answer is it's not far from optimal, but in fact it's not strictly the optimal code.
How come?
Because when you submit variable length code words to this FIFO buffer, it effectively acts like an MG1Q, right? Because like each input code word has some variable length and then some variable processing time, and the age ends up being almost the same as the average delay through the MG1Q. And this MG1Q has a second order effect that it has to balance the making the first moment, the service time, short versus making the second moment small. So the Huffman code just simply makes the first moment of the code word length as small as possible, but in fact the second moment matters. So there's been more work on this problem by Himanshu Tyagi and Parama Parag, and they have a paper coming out with a somewhat different model. The primary difference in their model is that their model is not lossless like this one. So in some sense, they have a more kind of age-centric formulation by simply saying we don't care about symbols that are lost. We'll just go to what is the most recent symbol that was delivered, and the result is different code construction. So another problem. Go ahead.
I guess I want to ask if, because I mean we know that Huffman codes are optimal. Is there a trade-off between sacrificing optimality in terms of compression rate in order to be better on the age?
Yeah, there is a trade-off, and the trade-off is that a different code which has less variability in the code word lengths, right, has a better kind of delay characteristic. That's the gist of it. So another problem we've worked on is caching of dynamic content. You have a remote server, and then you have a local cache that delivers objects, files, updates to these happy little faces on the right. And in between, you have a cache link that's slow or perhaps expensive. And what you want to do is choose at what rate each of these objects from the remote server is updated at the local cache. And you do that in order to maximize a weighted sum metric of the ages of things that are delivered to these smiling faces over here. And when you solve this optimization problem for the weighted sum age, you find out that the cache update rates of the individual objects, the rate at which they're transmitted over the expensive link, should be in proportion to the square roots of their popularity. And it turns out this problem is isomorphic to a file placement problem in content distribution networks that Cohen and Shankar looked at 2002, where they derived the same square root of popularity law. Yet another application we've looked at is mobile edge cloud gaming. You have a game client, it sends commands to a game server in the network. The game server streams video frames. And in this model, each video frame that's delivered is a status update. And the issue is that sometimes a frame isn't delivered on time. You're running at a fixed frame rate, and then you experience a frozen frame effect that you have to wait for the next frame. And the result is frozen frames increase the age. And you can use age metrics to identify kind of age optimal frame rates. And also there's an effect where there is an optimal amount of time that the game client should lag before displaying the frame. And you can optimize this lag for minimum age. And that was work with my former student, Mernaz. Okay, so that's kind of a big, long intro that we spent like most of this hour kind of trying to convince you that there's lots of things you can do with age. And all of those papers and many papers by other people that I haven't talked about use kind of the same analytical techniques. They look at updates, they look at an age process, and they generate this sawtooth, and then they try to analyze properties of this sawtooth. If you're analyzing average age, you're stuck with some version of this average age formula that involves second moment of inter-arrivals and a correlation term between inter-arrival time and system time. And I say relatively few papers have appeared since like in 10 years almost. I guess it's 8 years since this paper appeared. And I think the reason was because people would read one or two of these papers and be like, whoa, this is really hard work figuring out what this age is. Tony Ephremides once used the phrase that people working on this sort of had brute force ingenuity, that people who really love queuing would be like, I love this subject. These problems are really hard, but if I work really hard, I can solve them. Which is nice for a small group of people, but makes kind of the concepts kind of useless. So I found myself spending a lot of time working on trying to figure out a kind of better tools for doing this age analysis. And so if you kind of go back to square one, you always end up with this sawtooth process. The age grows, the age drops, the age grows. And essentially, this age process, or if you have a collection of them in a network, each component of the age, in the absence of something happening, simply grows at rate 1, right? It grows 1 unit of time per unit time. And then somehow the only other thing that happens is that when there's some kind of a discrete state transition, like a packet is delivered from one node to another, then the age drops. and that's the essence of what's going on. And so we looked around for machinery to analyze systems like this, and we found, oh, there's a huge literature on something called stochastic hybrid systems. And these SHS systems have a discrete state Q of t and a continuous state, and they have kind of a very powerful and general framework. Uh, um, it's so powerful that it's very easy to create stochastic hybrid systems that you can't really analyze. But in our case, things are much simpler. So the general framework of SHS is that in a state Q, in a discrete state, there's some stochastic differential equation obeyed by the continuous state. And then when you have a transition in the discrete state, you can have a jump discontinuity in the continuous state. And these discrete state transitions occur at some Poisson rate that is state dependent. So this is kind of a fancy way of saying, oh, in state Q, there's a set of transitions in continuous time to other states Q prime. And when you jump to Q prime, you have some transformation of continuous state. And so I've mostly followed this work by Hispania, but this is only one flavor of this sort of work. So in our case, the system is actually quite simple because the sawtooth is simple. You have a Markov chain Q of t that describes kind of where the packets are, like it might be the Markov chain for the Q occupancy or for the distribution of packets around the network. And then in going from state I of this Markov chain to state J, there's some transition rate associated with that state. And when this transition fires and you go from I to J, there's some matrix transformation of a collection of continuous age variables. So this A matrix is actually a binary matrix, which basically says if J is getting if there's some node here in state J that just got a new packet from some other node, then the age at that node is reset to the age of this update that was just delivered. So mathematically, in every state, age grows at unit rate, and then you have these transitions that that age is reduced when a packet is delivered. So to analyze this, there's a lot of machinery you have to use, and it involves sort of state indicators of tracking what state your system is in, and state probabilities, the expected values of these state indicators, and then some conditional age moments where you look at expected values of the age at a position J in the system weighted by the probability you're in a state. So the indicator, this combo depends on both the network state J and what state you're in Q. And you can do something similar where you look at conditional age moment generating functions, where you look at the expected value of a moment generating function of the age weighted by the state indicator. So the way to think of this is as a conditional age moment, and then you'll have a weighting term that is the probability you're in that state. And so when you build these systems, you in fact using kind of standard machinery of stochastic hybrid systems, you get a kind of a big system of first order linear differential equations. So the first equation with these 0 superscripts, this is just simply the differential equation for the evolution of state probabilities. And the second set of equations is if you're interested in the mth moment of the age, at various nodes. You get a set of equations for the derivative of the mth conditional moment in terms of the m-1 moments, and for the moment generating function at parameterized by the S, you have a slightly more complex system of equations that once again depends on these conditional moment generating functions at all the other states. The way to think of these things is they're really just generalizations of differential equations for Markov chain state probabilities. So the next step is to say, oh, I'm interested in the limiting expected values, and so you just simply set these derivatives to 0 and observe what you get. So when you do that, the first result in this paper with Sanjit Kaul, right, was that if your Markov chain Q of T is ergodic and has some nice stationary distribution, then you can solve for the average age with this set of sort of simple linear. So I should be more clear. If you then can find a non-negative solution that solves this set of linear equations that essentially constitute kind of age balance equations that generalize probability balance, then that in fact gives you the average age. The average age is the sum of these V bar terms. So essentially it reduces doing these age derivations, where if you've read papers that did very complicated things, to just doing some simple linear equation solving. The next bit of work we did built on this to say if the Markov chain is ergodic, has a nice stationary distribution, and the first moment of the age, the average age, exists, like you can solve those equations, then you can show that the moment generating function of the age, the stationary moment generating function, converges to this expression. Once again, it's kind of remarkably simple stuff. Pretty good. So then we applied this, see what time it is, to an example of a kind of a simple network. And it's there's a source, and at rate mu0, which usually you call lambda, sends updates to node 1, and each node in this chain is running a last come first served preemptive server. So an update arrives at node 1, immediately goes into service. Eventually updates are node 1 delivers updates to node 2, where if node 2 is busy, a preemption would occur there. And this system is in some ways as simple a network as you can build, because you only keep track of whether each node is busy or not. But in fact, it's pretty complicated. It says there's complex queuing. What is there's a complex arrival process. Like at each node beyond node 1, the arrival process is not Poisson, because at the previous node, things were getting preempted and deleted. And a node that sort of goes all the way, an update that goes all the way through the network to reach node N, in some sense was kind of a super lucky update, right? Somehow it managed to get through the system without getting trampled by all these other updates that are trying to preempt it from behind. So so in the simplest case, we have just last come first served preemption with one node in between, and so this is, you think, too simple, but this is a joke. So I've noticed that this service system is the same one they use on The Bachelor. The Bachelor sits on the sofa, the girl comes over to talk to him, and she tries to tell her story, and then this happens every episode. The next person, contestant, can I steal him for a minute? And and then the girl in blue preempts the girl on the sofa, and they never go back to the girl in black. She's discarded. This conversation is over. So in fact, this is kind of an important queuing system. So in any case, we had we used this average age analysis and did a lot of calculations and found, oh, the age at node n is just simply the expected service times of an update at each node, that the average age in this line network is additive. And this, I did this algebraically. For one node, you got this, and two nodes that. And frankly, I was kind of mind-boggled that this came out. And when it arrived, I thought I'd better understand this. And so maybe another year of work or two, we developed this method of looking at moment generating functions, and we applied it to this thing. And we saw, oh, the moment generating function of the age at node n was just the product of these exponential moment generating functions at all the intermediate nodes. And it turns out, oh, the age at node n is just in distribution the same as a sum of independent exponential random variables. And at this point, you're like, okay, this seems startling, but there has to be a simple explanation. And it turns out that, in fact, there is a simple explanation. So the simple explanation comes from thinking about at a node I+1, like z is the time since the last update at node I. And so the age at node I+1 is the age at node I at time t minus c plus c, because this is the timestamp of this was the age of the packet when it was delivered, and then it aged by this much more after you got it. So if in fact this age process is stationary and independent of this time since the last update, then you do some sort of trivial expectations, and you find out, oh, the age at node I+1 is the age at node I plus this z variable. And in fact, this z is really easy to understand. If in fact you think about node I and node I+1 having a relationship where updates from node I are instantaneously sent, as a point process as a renewal point process with y denoting the inter-update time, the inter-renewal time. Then in fact, this z that we talked about is the age of the equilibrium renewal process. And the age at node I+1 is the age at node I plus this age of the equilibrium renewal process. And this has a nice characterization in terms of the complementary CDF divided by the expected value. And in the case of exponential inter-renewal times, that deliveries of these updates, in fact, this is still the same exponential, as probably everyone knows. So so the exponential case was kind of a special case, but the general case of this preemptive model is that the age at node I+1 is the age at node I plus the equilibrium age of the renewal process. So so this kind of motivates kind of a new model for thinking about what's going on here. And we had a model before where we thought about this preemptive line network with very complex, an update replaces the prior update, and things get thrown away. But in fact, the way this system really operates is is that node, you can equivalently think of node I plus 1 every once in a while saying to node I, hey, give me your current update, give me your state, right? And it immediately gets that new update as a point process instantaneously. And it does this as a renewal process with time y. It samples, node I plus 1 is sampling the age process, the state process at node I. So what we're doing is sampling. We're not actually queuing. We're not, you know, we're not preempting or queuing. We're just simply sampling our neighbor. So if you build sample paths of these things, so for instance, this is the age at the first node, this black curve. It gets reset to 0 because it gets a fresh update, then it grows, and it gets a fresh update. And then the blue is the second node in the line, so his age grows, and then he gets a sample from node 1, and his age drops to the age of node 1, and then he grows, and at some point later he gets a sample. So these things, the subsequent age processes just kind of are growing and then sampling the age process of the predecessor node. So these are 3 sample paths, and now as kind of, you know, this general sort of approach to the status sampling network, because it didn't rely on kind of any Poisson assumptions or any exponential service times. You can use any general distribution. And so I did some experiments where the inter-update times are continuous uniform random variables. So not memoryless specifically. And so we built these sample paths and then sampled them to get age histograms at each of these nodes. And so at node 1, the age histogram is this nice triangle, and that's because the inter-update time was uniform from 0 to 6, and so the complementary distribution looks like this triangle. And then at node 2, you end up convolving 2 of these triangles to get a distribution that is the distribution at node 2, and essentially you just keep doing these convolutions and everything looks perfect. It's so I think on this graph I also have some central limit theorem approximations of the same mean and variance. And, you know, as you see, like by node 5, the actual distribution and the central limit theorem approximation is, I think, the black one. Yeah, pretty good. So so that's kind of the story, that this kind of very complicated kind of preemption kind of network, in fact, is really can be generalized, this idea of status sampling, where one node as a renewal process goes and asks his neighbor, well, give me your latest packet, give me the state. And it turns out it's actually quite a simple thing. So finally, I'll just wrap up and say, you know, we have this age metric, and I didn't make a big point of this, but you can utilize it for lossy systems or lossless systems, because it all that matters is the packets that are delivered and what age reductions they afford. Once you think about using this age metric, you have a variety of kind of minimization ideas about either matching the updating in terms of rate or policy to the network resources. You might think about re-engineering the system to throw away the old stuff. And then, you know, as a general idea, you have this sort of whatever you're interested in as X, you can ask yourself the question, well, what is timely X? And in my case, I've looked at updating and storage and a little bit of compression and caching but there are lots of other things still to look at. I would say, a big area that is of real importance is looking at sort of timeliness and edge cloud processing, right? Edge cloud processing, you can make lots of decisions about which things to process for client devices who, when they receive the result of your processing, view that thing as an update. So so in any case, this talk was really about two papers. The first one with myself and Sanjit Kaul that came out in Transactions last year. And the second one that develops this idea of moment generating functions for age and consequent distributions. It's in process, but new versions on archive. And anybody who's in the future listening to this talk, if you have an idea for something to work on, you can be like, well, if people looked at the age for this or that, and you should go to this Yin Sun at Auburn. He has a web page with like categories for each different sort of application area, people using age, and you can quickly find out what papers on age have been written about whatever it is you might be interested in, and if you have a category that isn't there, then you almost certainly have something new to think about. So I think I'm all done.
Thanks a lot, Roy. This was very interesting. So we have time for a few questions. I don't know if anyone has questions. So we're gonna clap.
Thank you, Anand. Ali.
So I don't know if anyone has questions.
Just a quick one. So Roy, if I understand, the arrival process is somehow independent of the communication process, right?
It doesn't have to be.
Mm-hmm.
So in the earliest work, we looked at systems where, you just submit arrivals at some rate. But then in later work, we were like, oh, you submitted arrival and you get some state feedback about like when it's delivered and what the status of your system is. And there have been quite a few papers that look at like controlling the submission of arrivals based on some kind of network state that might, the energy harvesting state, as an example, right? Lots of papers about timely updates by energy harvesting sources.
Yeah, that's exactly what I wanted to know, whether there's a work on the feedback mechanisms, how they could intervene with the arrival process. Thanks.
So there's energy harvesting is one category. Yin Sun, whose picture is, I think, still up on the slide. He's actually written some papers where he tries to connect the state of the process that the source is actually updating about, right, and make decisions on submitting updates based on that state. And in some general way, he has results that say, if you're trying to minimize mean squared error of some estimator, you can do better by, figuring out at the source, well, what is the error at the moment at the monitor, and now should I send them an update? But a time-based system that just simply uses an age metric can be actually pretty good, right? I think there's a lot of work to be done to figure out when you can use a time measurement like age as a proxy for something application specific.
That's right. Yeah, thank you.
All right, so thank you, Roy, again, and thank you, everyone. And everyone who's interested will be able to see the video on YouTube. probably if you're watching it right now, and then can comment or send you questions. Thanks again, everyone.
Hey, thank you for watching.